Hello, everyone. This is Professor Ma, and this is the introduction to the section on triple integrals. Okay, the topic we're going to cover, basically, we're going to cover triple. We'll start out with a triple integral over a box. Then we generalize that to triple integrals over something we call regular solids. Okay, so we'll start with the box. And so this is the way we usually write a rectangular box in a set notation. In particular, what I meant by that is, if I choose any number x over here, if I choose any number y in here, then I choose any number z in here, and then these points x, y, z will be somewhere inside here, okay, in the box. And that's what we mean by cross over here. Any number in the front goes with any number in the second set. If there's another cross, then third sets, then it could be any numbers on the third set. And of course, there's a description of this box. And notice basically there's no difference if I were to switch the orders of the variable and switch the orders of the intervals accordingly. So this can be CD cross AB, right? And this is Y is actually by specify the order. Okay. Now we're going to have a function defined, continuous function defined on this box. That's not the motivation. Think of it as this box is as alloy or some of the mixtures of different metal, but not evenly. Some was heavier, some was it's softer, so have different mass, different density at different place. And we want to calculate the mass of the entire. Okay. So what do? We cut the boxes into tiny little boxes, and we're going to estimate the weight of the mass of each box. And the way we do it is we select arbitrarily a point inside that little cubicles, and then we find out what the density at that cubicle is, and that will be h of this point, right? H is the density functions, and then we multiply that density times the volume of the box, and that's the mass of that little cubicle. And then we keep cutting the box into smaller and smaller cubicle and do these estimations more and more accurately. And the limit of that is the mass, total, the mass of the box. Okay, and we write that as a triple integrals of the density function over the volumes, over the differential volume. That this remind you the way we cut it. So that means this refers to how do we cut the solid. So we cut the solid into little cubicle. Therefore, the little solid, the way it's cut is dx, dy, dt, and it doesn't matter which way we will write it. Okay. And so how do we set up the triple integral over a box like that? Since these box descriptions, it was the intervals like that, then basically we can set the dv in terms of dx, dy, dz in any way we want to, because this is a box. This for all constants. Okay. In other words, if I were to set this to be 1, density to be 1, I should get a volume of the box. And notice what I got. If I integrate 1 with respect to x, I will get b minus a. Okay, and I'm going to integrate that with respect to y. Next one, and I will pick up times d minus c. And then integrate with respect to z, I will get f times f minus z. I get this the volume of the box. Okay. So, And notice in this case, also it doesn't matter the orders of the way I set the integrations. Again, because this is a box. There's 5 other variations. There's 6 altogether. So particular for a box, again, if I want to set this way, then the way I set it up is, okay, the last one's dy is going to be y is from C to D. So y go to C to D, and then followed by dx, x goes from A to B, and then dz is z go from A to F. Okay. Then you put h in there. So it follows these orders. So I'm doing this backwards from the outside to inside. That's in the setup. Now, how do I do this if the solid domain is not a nice box like this? Well, then we set some restrictions on the solid. Basically, we restrict the solid that we're going to have. It's like as a top, as a bottom. Okay, it could be, it could be closed like that, or it could be, separated. Okay, and like this. Okay, but they don't really have to meet like that. It could be the tops like this, and but it sits over and precisely over the bottoms. Okay, basically it's like a shell. Okay, but the shell could be, the two pieces of shell could be pulled apart. One's on top, one's on the bottom. Okay, the top function is z equal to f of x, y, and the bottom shell is for the g of x, y. Okay. And this way presented, the shell is facing the open, close in the z direction. So we call this shell, this solid, z regular. Then you can think this out. Then if the shell is placed this way, I can place shell this way, and then this will be x regular, and this will be y regular. So there are 3 different ways to present the solid. This is the one we, the most familiar with, start out with. So this is z regular. In particular, then it sits over the base D, and then the D itself in the XY plane has 2 types. It could be the X regular, Y regular, right? And so we did this, the type, the type 1, type 1, type 2. The type 1 is in the XY plane. The domain in XY plane is defined by 2 functions: upper function, lower function. Upper function here is y to f of x, right? And the lower function is the one on the left, y to g of x. Okay, so I can write a d first. The key point over here is you write that domain first, as in the set descriptions. Then for the last, to describe the solid in total, then I have to give a z value for the third component. That you just attach the z between the 2 functions f and g. So z is going to go from bottom, g go up to f, and so this is the set descriptions of this z regular solid. Okay, and here are some examples of the descriptions. So in here, all we want to do is just describe this solid, these corners of the wall, this tetrahedron that we chunks that's in there. So we want to describe it as type 1, type 2. This is x in the z regular, okay? And the type 1, type 2 is talking about the little base on the floor, the xy plane as type 1, type 2. So first we get the coordinates over here on the, so then we can, then since we want to talk about type 1, type 2, we want to talk about this domain, so type 1 is you have these two functions in X found on top. So for any X type 1, for any, you say type 1, immediately it goes, oh, from here, type 1 going to 0 from 2. It talks about X first. Then the functions of Y is bounded between X, in this case, 0, and then you solve this for the equation for Y is equal to whatever C minus 3 half X. So that's a description of type 1 of the base of this solid. But I want to describe the whole solid, so I need a Z component. You just take out the Z component. The Z go from the floor, Z go to 0 up, oops. Z go from the floor, Z go to 0, goes up to whatever the points up there is, that satisfy these equations. So Z, you just solve the equation for Z, and that's where Z is. So this is a Z regular type 1 description. I can ask you for Z regular type 2. Then if it's type 2, okay, then where do we start? Or immediately we start with Y. Because from Y here, X over here, Y is between 0 and 3. Then we need a description for the X go from what? X go from 0, then X go from 0 to what? Well, then I need these functions in Y. Okay, so let's write it out. 2 minus 2 for Y, then we take on the Z. Okay. So the Z is the last variables because it's Z regular. And you can imagine we have X regular, Y regular. Here's another one, Z regular. So I'm going to write the X and the Y component first, then write the Z component. So I'll let you go through this. Okay. So type 1, this is the in XY plane description. Then you put in the Z, which is going from, in this case, for any points in here, the Z goes from, it goes from here, inside goes up to here, so the Z goes in this direction, in the solid, okay? From the surface up to Z equal to 2. And this is type 2. If I have a density functions now over Z regular, in this case actually type 1, the solid, because X first, Y, that's type 1, so the Z regular type 1. How do we set this into iterated integral? So I can actually do the algebraic computations. Okay. Again, the way we set it here is we set it up outside. Okay. Now, for any problem that has a definitive answer, like the total mass, the total heat, that you will have to arrive at a definitive numbers as answers, then your last integrations of iterated integral must be numbers outside. You cannot have some functions out here, and you can't have x is equal to like 2y or something like that. No, if the answer is, it's going to be a number. So the setup must have numbers. The last two must be a number. You plug in the x, then you calculate, you get a number. Okay, and that's this first from the first set description. That follow the middle, the y go from the bottom to the top, then the z thing go from the bottom to the top. Okay. Then this is the type 2 descriptions, and then the integral setup will be, again, you will read the y first, and it goes outside, and the y, and the rest of this stuff is to be set related to these two. Okay, in these layers. And if you set H to be 1, you get 1. Okay. Here, find the triple integral of 2 times z, where the z is where the over the triple integral where the domain is this wedge of cheese. Okay, so in this, so for every point in here, for example, this point where is equal to 1, okay, x0, 0, 1, okay, and the function f is 2 times z, so f of this is 2 times z will be 2. And this point may be halfway down. This is even some point over here will be something z is 1/2, and then this point f of t will be 2 times a half. 2 times z is 1. So it's a well-defined function. What's the oops? Let's all that. I want to describe this. Oh, by the way, when I get this wedge shape, well, x squared plus z squared, if I look at it, this is the z. If I look at xz plane, and that's a circle. So this is a circle in the xz plane. Okay, z. And y can be any number. Since it's not in the equation, hence this is the x squared plus z squared 1 is the cylinder. Okay, with the y-axis coming down the middle. Okay, then I slice it. Yeah. So in particular, it's in the first one. Okay, and so this is the descriptions of the volumes and then the setup. So start writing out the integral from the outside x dx 0 to 1 dx outside. Okay. And then dy and integrate. So leave the algebra up to you to check. The integration gets, because you're going to integrate it 3 times, so things gets picked up, the power gets picked up pretty fast. So it's by calculate by hand sometimes slightly more. Okay. Here's another problem. Again, this is type 1 description, Z regular type 1. So again, I set this up to you. Now, remember we say type 1 is that the Z of x, y, z, and so the type 1 is z between z f of x, y, and g of x, that shell. But there's 2 other ways to do it. I can put the shells this way. Look like that. Okay, what? Notice x and y. In meaning, then in this case, if I look at which way is facing the y. Okay, so in other words, and this is what I'm drawing here. This shell is actually facing this way. This is our traditional x, y, z, and my eyeball is over here, looking downwards. I don't know if that makes sense. So that's what it looks like. So this is the orange part, or the yellow part, the downstairs, the purple part, and that's what it looks like if the eyeballs there. Okay, and then of course the plane underneath here is XY plane, and there's the screen back over here, and that's right over there. Okay, and then you can see then the project these are the domain is going to sit over the XZ planes now, and that let's suppose we think of these two functions as bounded by Fz and Gz on the bottom. So in other words, I'm going to calculate what Z is first. So we start with Z, goes from what to what, A to B, and then d squared X, then d squared Y. Okay. So again, there are two types here. Okay, because the other type could be that I view this base as the following, as this is the top versus these on the bottom here. Okay, then I will be looking at X goes from something to something. X goes from. So I will start X goes from C to D. Okay. Then I will describe the black line and the blue line. But this is facing the other way. So that's a description. So then the triple integral, then I again start from the first Z, some set of numbers. That must be the outside integral Z from number A to B, and then the next is X. This functions trapped between f little g. So X go from little f to little g, and then Z, and then the Y go from XZ, F of capital F to capital G. Then you stick with this one. You cannot remember this type. You cannot change the order of integration because all these limits are not constant. So they describe a particular solid in a particular fashion. If you search it, a lot of times it don't even make sense. Okay, if you search it, even if you search the orders, it's a different solid. Okay. So this you cannot switch easily. Okay. In other words, it doesn't make sense for you to switch, put this XZ in here and put this X over here, put XYZ over there, and then let's start out with the DZ. Because you have to justify your order by coming out with a correct set descriptions, correct description of the domain of the solid. You have to justify it. And that has an order. When I have X regular, I let you read the rest. Then these go through different type of orientations and setups. Yeah, the rest just try to visualize, keep track of what you're looking at. Yeah, that's a very interesting problem. So yeah, that's it. Bye bye.